Okay, in this lecture, we learn about phase shift keying. Phase shift keying have M-array version in which we have M phases, and we have the binary version of it in which we have only two phases, which is 0 and 180 degree. So we know that the carrier has some phase, and that phase is modulated by 0 and 180 degree phase. Or in radians, we can say that we have 0 and 2 pi radians per second. So you can see the waveform that is in fact having an abrupt change at the start of every symbol. So that change is of 180 degree in binary PSK. So the information is in the instantaneous phase of the carrier. So that instantaneous phase can be calculated by dividing 2 pi radians by m. So in our case, we have I is equal to 1 and 2. So for 1, its value is 0, and for 2, its value is 2 pi. And we can go up to m for depending on the number of PSK we are using. Normally, we have 8 PSK and 16 PSK. So if we are using a rectangular pulse, so the G of t is in fact is 2 by TB under root. That is in fact for a rectangular pulse, and the amplitude of the pulse is EB by under root. So means that we have a pulse shape having this value, and we have the symbol energy into EB by under root. So the envelope of this phase shift keying is constant, and there is no fluctuation in it. Or this constant envelope has value of 2 EB by TB, and this is in fact is the carrier phase changes abruptly depending on the number of values of M. So we can have the duration of the symbol is from 0 to TB. So we can also write it in phase and quadrature phase component. So the in phase component has represented by cos of omega ct, and the quadrature phase component is sine of omega ct. So there is no sign here. So in fact, this is in fact is the in phase component, and this sine of omega c t is the quadrature phase component. So we have only two basis function, phi 1 of t and phi 2 of t, irrespective of the number of phases we are using, or irrespective of the number of symbols we have in PSK modulation scheme. So this basis function have 2 by t under root shape and 2 by t under root shape of the signal. And so we simplified the symbol in this form, that under root e cos 2 pi I minus 1 by m psi 1 of t, and similarly for the quadrature component. So in here we are using the concept of orthogonal basis function, because the orthogonal basis function, you know that the correlation between these two basis function is 0. That's why we chooses the projection of the signal over the first basis function and the projection of the signal on the second basis function. So we have m array phase modulation depending on m is equal to k, and k is the number of information bits mapped over the symbol. If m is greater than 2t, so we take the signaling interval is equal to ts seconds. But when we are using BPSK, ts is equal to tb. So we have the very common type of phase shift keying, which is the quadrature phase shift keying. And in quadrature phase shift keying, we have several variants of it. In this, we are using the value of m is equal to 4, and the value of k is equal to 2. That 4 symbols, each one is mapped by 2 bits. So the instantaneous phase is, in fact, is 2 pi I minus 1 by m. M varies from 2, 4, 8, 16, or like this. So we have the variants, but the performance of the system will be degraded as we increase the number of symbols. So because the decision boundaries are very close, so we can overcome this by using gray coding scheme. So, but whatever the constellation scheme we are using, we are restrict the demodulation depending on these two basis function, and the modulation is also based on these two basis function. So the quadrature version is equivalent to 2 BPSK, and the performance of the quadrature component, quadrature PSK, is same as that of BPSK. Why? Because in fact we are incorporating the quadrature component which we are not using in binary PSK. So the instantaneous phase which we calculate from this formula is, in fact, is 0, pi by 2, pi, and 3 pi by 2, right? So the modulated signal of this QPSK is, in fact, is written here. So if we calculate the symbol 1, so we have phase 0, and then we have phase pi by 2, which is equal to minus sine omega ct. So again we have the component which is pi phase and equal to minus sine omega ct. And when we have 3 pi by 2, we have the component which is equal to sine omega ct. So we have, in fact, two in phase components, which is plus cosine omega ct, and we have minus cosine omega ct representing by phase pi, and we have minus sine omega ct representing by plus pi by 2, and plus 3 pi by 2 is plus sine omega ct. So in fact, symbol 0 and 2 are represented by in-phase component with 0 and 180-degree phase change, and symbol 1 and 3 are represented by 90 and 270-degree phase change. So if you want to see the corresponding waveforms, so these are the corresponding waveforms that in fact the starting phase is something like this, and this, and this is in fact is changing. So this is in fact is what we make a change is that this is gray coded because we have 00, and then when we move to S1 there is a 1-bit change, and if we move to this S3 we have 1-bit change. So here if we move from S2 to this way and we move to this way, so both we are changing only 1 bit. Or if we are considering S1 and we choose this way and we are moving this way, so we are changing 1 bit. So if we are moving this way and we are moving this way, so again we are changing only 1 bit of the constellation. So this is called gray encoding because it enhance the performance by reducing the probability of bit error as compared to the probability of symbol error, because one symbol in error means there is only 1 bit detected erroneously. So you mean that instead of S0, if we have the decision boundary up to here, and if we detect S1 or if we detect S3, so we have only 1 bit in error instead of 2 bits in error. So its error probability is same as like of BPS. So here 2 bits are transmitted per symbol. So the symbol duration is twice of the bit duration. So we are in fact aligning the I and Q channels basis on the phase transition occurs every TS symbol. So the QPSK modulated data is represented in phase and quadrature phase form. So we can say that if we know the value of this in phase component, so we can calculate this value in numeric form. So we can also calculate the value of this in numeric form. So the numerical values multiplied by this cosine and sine component will help us to have any form of constellation plotted in phase and quadrature phase component. Later we see on that the every constellation can be plotted, I means in 2D form. So this is in fact the distance between the QPSK symbols. So in QPSK, the symbol energy is the symbol energy is in fact is ES under root, and that is constant wherever it lies in a circle. So I can say it, this is a unit circle and having coordinates 1, 0 and having coordinates 1, 1 and having coordinates -1, -1 and having coordinates -1, having coordinates 0 and -1. So this is a unit circle and the symbol energy is constant. What about the distance between these two symbols? Because the distance helps us to calculate the performance of the errors. The error probability depends upon the Euclidean distance between these two symbols. So the distance between any two symbols is constant, that is under root es square plus under root es square and under root of these two. So this will 2es under root. So that is constant. So coherent detection of BPSK, the coherent detection of BPSK is almost like the same way we are doing for binary ASK, and it is multiplied by the locally generated carrier, and low pass filtering it will, and after sampling we make a decision of the symbol transmitted. So this is almost the same we used for binary ASK, because it is binary PSK is also one dimensional, and we are using the same technique we have adopted in binary ASK. So also the modulation and demodulation followed by the match filter pair, and this is in fact is the match filter pair, which is designed over a specific pulse shape, or we may also call it the pulse shaping filter. So what about the coherent detection of QPSK? So in fact, we have a received signal which is S naught of T. So we received S0 symbol from the constellation. We multiply it by both basis function, and we will have this basis function is in fact is 2 by T under root or A cos of omega naught T, or a sine of omega naught T. So multiplying it by a cosine of omega naught T, so you can see that is in fact is a square Ts by 2, because when you multiply it by 2 by T under root basis function with the received signal, so you will get the output is equal to Ts by 2. So this is in fact, we represent this as L naught, and we represent the quadrature component is missing, so we have the zero result. So we have two possibilities, either we have L naught or we have zero. So we have a lookup table on the basis of the in phase and quadrature phase component of the receiver, and we have the combination for S naught of T is L naught 0, and we have the corresponding lookup table for S1 of T to S3 of T. So L naught here is a squared Ts cosine pi by 4. So what about if we are using the constellation, like we have pi by 4 initial phase offset. So if the initial phase offset is 45 degree, so it means that we start from the pi by 4 phase, and we end up by the phase here, which might be 7 pi by 4, right? So here in this case, if we have the offset like this, so we have L naught component for S naught of T in the lookup table. So how we calculate this? That first we have the Z1 of T and Z2 of T calculated, from multiplication of the received signal with first basis function and second basis function. And then from the lookup table, we look up the value of 0, 1 and 0, 1, 0, 1, Z0 and Z1 from the lookup table. And then we decide what is the transmitted symbol. So this is the case we modulate the signal. So this is in fact what we are doing here is that this is in fact is the after carrier recovery, we have carrier, in-phase carrier, and we have the 90-degree offset. We have the 90-degree offset in the carrier, and we send it to here. So this is the in-phase component after match filtering the signal. So we get the output of the signal, and then we have the comparator, or the comparator will decide whatever we have transmitted, and then we have serial to parallel conversion. Because for mapping the bits, we choose 2 bits, 2 consecutive bits. In that way, that we convert it into the parallel. We send 1 bit to the in-phase branch and 0 bit to the quadrature phase branch. And we modulate these 2 bits with opposite carriers, and then we transmit these over the channel. So after we have the signal received, so we need to perform parallel to serial conversion based on I and Q phase modulation. So in short, this is the review of the what we have learned so far. It is just like 2 BPSK scheme, and we have 2 information bits mapped over the 4 different states of 4 different phases. Each symbol corresponds to 2 bits, and they are gray encoded. The error performance is same as like that of BPSK, because in BPSK we are wasting the quadrature component, and we have the general expression with some initial offset as well, that we can set some initial offset in QPSK, which is of pi/4. So we may have this initial offset 0 in some cases as well. So if the initial offset is pi/4, so you can have the numerical values calculated against it is this. This helps in modulation. So if we have the numerical values assigned to these carriers, and then we modulate these 2 bits, so the in-phase and quadrature phase component will generate a carrier with this phase offset. And if we have in-phase and quadrature phase component with negative values, so we have the phase calculated by this is 5 pi/4. So in QPSK signaling, as I said, that first we divide the bit stream into even and odd bit stream, and then we have map the bit stream D0 by dividing it 1 by √2, and we divide the bit stream dq by 2 by dividing it 1 by √2, and we set the initial phase to pi/4. And you see that the S of t have some value theta I of t, which depends on the value of this signal. And you look on the diagram later on that if I have here, okay, maybe the diagram is missing here, and I can show you later on that this will generate a carrier with some offset like pi by 4, 3 pi by 4, minus 7 pi by 4. Because when you divide the bit with this value or this value and you generate a carrier, so it has the corresponding offset. So di of 2 amplitude modulates the cosine function with amplitudes +1 or -1, equivalent to shifting the phase of the cosine function by 0 or pi, producing a BPSK waveform. And similarly, the things doing with dq of by t by yielding another BPSK, which is generated by sine carriers orthogonal to the cosine. And the summation of these two orthogonal components will generate the QPSK waveforms. So this is in fact is the combination of EI and DQ of P. So this is in fact is the +-1 bit stream, or you can say that this is the bipolar energy coding we have assigned before transmitting. So this is in fact is the symbol duration is prolonged to 2t, and symbol duration is prolonged to 2t for both even and odd bits. So what even and odd bits we have generates this duration over to 2t, and then we modulate the signal by this 1 by √2 cosine omega naught t plus pi by 4. So here the both value are +1. The first bit is both +1. So the value is 0.707 and 0.707. So what will be the value of this theta of t? We just go back to the lookup table. So this value will be pi by 4. This value will be pi by 4. So the value of this would be theta of t would be pi by 4. If the initial phase pi by 4, so the value of theta is theta of t will be pi by 2. Similarly, we may have other bits like other combinations we have seen for 0, 1 and for 0, 0 and 1, 0. Why? Because this 0 is represented by 1, and this 1 is represented by -1. So, but the problem with this in QPSK is that we have a phase shift of pi. So the transition at the time of next symbol is pi, and this pi shift will make it difficult for a non-linear power amplifier. Non-linear power amplifier used in satellite communication. So this is unsuitable for satellite communication. So basically, to avoid this 90-degree phase shift, or avoid the ±90-degree phase shift, we want to use the offset QPSK, which is called the staggered QPSK. and this have relatively more constant envelope after pulse shaping. So this scheme is used in CDMA standard IS 95 for the reverse link. So it is right to understand that why a phase shift of T here, a phase shift of T here, because we divide the even bit stream and the odd bit stream. So basically dividing, shifting it to T duration, making it an offset of T duration. So this helps in transition of this helps in transition of E minus J omega naught T. This will incorporate a delay of E minus J omega T, or due to this T time shift. And that shift is of, in fact, is pi degree. So to avoid the phase shift of to avoid the phase shift of plus minus to avoid the phase shift of 180 degree. We have a phase shift of plus minus 90 degree in this, instead of the phase shift of pi in QPSK, which is 180 degree. Later on, we see the waveform of this. So this is the, in fact, is the delay of serial to parallel conversion, and we have the delay of half symbol duration, and then we do the same process, and we perform the QPSK signal. So this QPSK signal has the output waveform with 90 degree, plus minus 90 degree transitions at the start of symbol. But in QPSK, we have a transition of 180 degree as well. So if you see the transitional waveform, so over the constellation plot, so we have the OQPSK having only 90 degree transitions from each symbol to symbol, and this helps non-linear power amplifiers, and that is useful for satellite communication. But here we have this and this transition, which is of 180 degree. So that's 180 degree transitions are make it unsuitable for non-linear power amplifier. So you can see that if the transmitted waveform, if the received waveform are plotted, so they have, you can see the phase errors as well, or you can see that there are no zero crossing here. but in QPSK there are zero crossings here. So this is the ideal plot. Bandwidth of OQPSK is 90% bandwidth is 1 by TB. So that is in fact is sufficient for communication, and bandwidth requirement are very good. So envelope fluctuations are very little, or so QPSK and OQPSK have same power spectrum in the linear channel. So this is the main things which we can learn about staggered QPSK or OQPSK. So there is another variant of QPSK which is pi by 4 QPSK. So the pi by 4 QPSK is in fact is having transitions of plus minus 45 degree. So you are surprised at how to perform this because this cannot be done by a single constellation. It has some dual constellation. One have initial offset with 0 and the other have some initial offset set to some other different point. For example, we have the initial offset here is pi by 4 for path A, and for path B, we have the initial offset is 0. So, but in fact, we have the path A for A constellation and path B for B constellation. So, for example, if consecutive 0, 0 and 0, 0 will come, so it will transmit A1 and then transmit B1. So if there is a consecutive stream of zeros, so it will continuously transmitting A1, B1, A1, B1, A1, B1, A1, B1 in that way. So if we have a bit sequence like this randomly chosen, so this bit sequence will be transmitted 0, 0 for, let's suppose it will be started from A1. So it will be started from A1 and then we have 0, 0. It will be started from B1 and then we have 1, 0. So 1, 0 will be started from A. So it will be A4. So in that way we goes on, and one is from A constellation, B constellation, A constellation, B constellation, and this is the way AB constellations. So the effect is that we have only pi by 4 transitions in the received constellation diagram or the received waveform plot. So it has no zero crossing. So you can see this if I am able to. I need to rotate it, but maybe I just want to show is that there is no zero crossing and all the transitions are, there is no zero crossing, and most of these transitions are in that way that it not passes from 0. So this is helpful for radio power amplifiers. So this is something we learned about QPSK, and next we learned something about QAM, constellation, and some other modulation scheme. So thank you very much for being here. Uh, Thank you.